don't know. Oh, okay. I probably have to zoom back out.
It's the expedited presentation.
See if we can repair the microphone. Good afternoon, everyone. This is the second meeting of the Path-Aware Networking Proposed Research Group. We're waiting a couple of minutes for people to file back from lunch. Sending the blue sheets around. I'm Brian Trammell, co-chair.
And Jen Clark, co-chair.
Okay, so this is a, oh, gotta, right, focus. This is an IETF research group. The IETF intellectual property rules parallel those of the IETF. Anything you say here is essentially an IETF contribution. You should be aware of rules about disclosure of IPR that may apply to anything you say here. So our agenda today, we're going to do a little bit of, actually, you know what? We're going to do a little bit of setting up my computer so I can do mirroring because I can't actually see anything from the chair here. We are going to do a little bit of review of how you set up a display on a Macintosh. And we are going to go to arrangement and we are going to do that and life will get much better for everyone. Woo! We're going to do a little bit of a review of sort of what the concept is, what are the questions that we're trying to ask and answer here. And then we have a set of invited presentations from Chris Pappas talking about methods for path dissemination in path-aware networks, and from Laurent Schwa talking about interfaces for path selection. So the first is, okay, so you have a network that knows something about its paths. It's going to take information about those paths and put them down to the endpoints so they can do something with them. This is sort of a mechanisms a discussion. And then once the endpoints have this information, what can they do with it? And that's more what Laurent's going to be talking about. Yeah, as we pointed out, one of the reasons that we're, as we pointed out the last time, one of the reasons that we're interested in this area in research is that there's a lot of work going on sort of in and around the IETF that begins to give us the ability to see a future where we have endpoints that are aware of their paths. And one of those bits of technology is provisioning domains. So Eric Finke will be talking about that. And then we have Sabine Randriamasi talking about Alto. Xingwang Zhao, I'm messing up all of these names, I apologize. Talking about a particular application of path awareness, specifically to congestion control. Since this is a proposed research group, we have a lot of time at the end for sort of like general discussion. One of the things that we're looking for here is interest in this topic, sort of at the interface between research and the IETF. Sort of what should we be looking at as chairs for the agenda for next time? Is there interest in working on, any documents talking about frameworks or looking at things that have already been done within the research group? So we're going to have a relatively, hopefully a relatively long and interesting discussion about that. So.
I think we still need meeting minutes taker and JabberScribe. So sorry for interrupting, but
Yes.
we're looking for volunteers, please. JabberScribe.
JabberScribe, thank you, Allison. And minute taker. Have I seen Tommy? Yeah. Can I get you to do that for me? Thank you very much. See, if you get good at it, people keep asking you to do it. That's the problem. I owe him like 3 or 4 beers anyway, so it's good. We've identified a common theme. This list of working groups, BOFs, and so on is not meant to be exhaustive. So if we missed out on yours, please don't feel bad. Of sort of path awareness and a lot of research sort of going on around the edges of the IETF. The obvious one here is MPTCP. As I understand it, there was just a lunch meeting of people trying to figure out how to do rebinding in a multipath friendly way for Quick. So that's not what Quick is working on. Multipath, they're not working on multipath right now, but that is a future development. Hybrid access approaches, path control approaches, dynamic interface and transport selection, and then path signaling work. So the fact that there's a lot of this work and nothing like an architecture or a framework around how you would put it together, architectures and frameworks not really what the IETF does, but this did seem like a theme that a new research group should explore. So for those of you who have no idea what I'm talking about, because you were over in ideas the last time we had that was an unfortunate conflict. As I understand it, we have an unfortunate conflict this time with the routing working group. So at some point, we're going to have to actually get the routing people in here. This is sort of what the internet looks like right now. You have, an endpoint, and that's not working at all, and another endpoint, and you send a packet to one of your gateway router, and that knows how to forward it based on some control plane information that is, distributed or centralized, usually distributed, but you can think of it, you can abstract it away as just sort of the control plane tells the forwarding plane what to do, and the forwarding plane does it. The endpoints don't have really any control here about where the packet goes based on anything other than the destination address. In a path-aware internet, you have the control plane in some way is pushed all the way to the edges. You have endpoints with protocol stacks that are path-aware at each end of the network. And can cooperate with the routers in order to select paths. So here you see you have path-aware stacks on, the colors don't look great there. So you have a path-aware stack on either side of that, and they can select multiple paths through the network that are joint or disjoint at various points. They have enough information about those paths to be able to make informed choices about which path they want to send stuff down. So yeah, again, what's interesting about path-aware networking, obviously the routers are aware of the paths that the traffic is taking. We solved this, it's BGP, right? Well, not really. We're interested in extending this to the edge. So discovery of paths, explicit association of properties to paths by endpoints, and endpoint selection of paths. Since we notice this is happening anyway in things like MPTCP and other multiple interface work, we figured that we should be explicit about it. This research group has one document that I wrote, Draft Trammel Panrg questions. This is essentially just a list of open questions. This is not anything from the chair. This is just, I'm interested in this topic, and this is what I think the open questions on that are. Please have a look at it and let us know on the Panrg list if the questions there align with what you think the questions in this space are. So we also intend that kind of as an introductory document to this work for people coming in from outside the research group. So if you are coming in from outside the research group and you try to read that document and you are completely confused and have no idea what I'm talking about there, that's also useful feedback. We had one suggestion in Prague, because we were talking a lot about, especially with Olivier's presentation, a lot about prior work in this space that was especially focused on the transport layer and how it tended not to work. It might be useful to have a catalog of failed transport layer signaling approaches, just a quick document that says, don't do this, that didn't work, don't do this, that didn't work. But also with some information about like, don't do this, that didn't work, and here's why, right? Like not just complaining about stuff. I understand we like to complain a lot in the IETF, but sort of looking at ways for like constraining the space for path-aware approaches so that we can make a little bit of progress here. One question that I'd like to ask in the discussion phase today is if there are any other documents that people have either energy to write or think that other people should have energy to write. And we'll try to find, as chairs, we'll try to find, match ideas and authors to things that we can do here. We are considering proposing a workshop on path-aware networking for SIGCOMM 2018 in Budapest. If this were accepted, this would replace our fall 2018 fall 2018 Panrg meeting. The fall 2018 meeting, I think right now is tentatively scheduled for Asia. I hope we'll narrow that down at some point before we have to buy plane tickets. So this would essentially replace that meeting, and we'd have it in Budapest instead. So the call for papers for this would be derived from the proposed research group charter. There's actually a draft of that. If you're interested in serving on the TPC for that, please. Thank you, Aaron, for your interest in serving on the TPC. Thank you, Spencer, for your service.
Aaron Falk, I'm just wondering, it's been a long time since I've been to SIGCOMM. Do they have remote participation at workshops? Because I don't think I won't be in Budapest, so I'm just wondering, will we have the opportunity to follow
remote
along?
Participation? Yeah. Not as I understand. They have no support for that, right? We can stick people on a Skype node in the corner, and your experience will suck.
Okay.
Yeah.
Answered my question.
They do have remote presentations. They have Meet Echo at SIGCOMM now?
In the workshops?
Oh, in the workshops. Oh,
Good to know.
Cool. Okay. So thank you. So yeah, let the minute show that Lars corrected me because I don't know what I'm talking about.
Lars Eckert is a treasurer for the SIG. If you put in the workshop proposal and in the requirements that you want from the venue, you put that in, they will budget for it if they can get it. I mean, they might say that it's not possible on Mondays, and then you will need to decide whether you still want to hold a meeting. But if you put it in you need to put it in the proposal because otherwise it won't be in the budget and it won't happen.
Yep. Thank you very much. I'll go edit the proposal then. Spencer.
Yeah, Spencer Dawkins. I'm actually got up and walked slowly at the mic, so this is about the previous slide or two back where you were talking about what. The catalog of failed transport layer signaling approaches. That seemed like a really useful thing to do, and if it is helpful for me to collect those experiences, I can do I can do 2 or 3 of them from my own experience. But just to start collecting that and let other people send me email and do it on list or me personally, either one. I'd be happy to do that if that's okay with the chairs.
Please do. So we expect a draft Dawkins Panrg. Please don't do this.
Please don't.
Dash do dash this. Yes. Excellent. Thanks, Spencer.
Yes. Thank you.
And I think that's all I have for my chair slides. So if you're interested in helping out with the workshop, we are even just looking for people who are interested in the area who would be willing to review papers in this space. One of the things that you need for a good workshop proposal is a credible list of people for the TPC. So please do send that to, I guess, Panrg chairs at IRTF.org should work. Allison, do you know if we have chair aliases in the data tracker? Yeah, we have chair. Yeah, oh yeah. Okay, we've used that. Okay, good. Yeah, never mind. We're good. So yeah, please send to Panrg chairs at IRTF.org. Interested in serving there. So thank you. Next up is Chris Pappas. And I will switch you over to Keynote.
Okay, good afternoon, everyone, and thank you for coming. Sorry? Okay. Okay, good afternoon, everyone, and thank you for coming to my presentation about dissemination of paths in path-aware networking. So I will start by the motivation of the path-aware networking research group and stealing from the Panrg agenda slides from IETF 99. One of the questions that this research group wants to answer is how does path awareness extend to the edge? And by edge, meaning the endpoints. So in order to answer this question, there are many other sub-questions to be answered. For example, how do endpoints discover paths? And more specifically, how do endpoints discover paths in a scalable manner? And how do they react in case of a failure in the network? Another question to be answered is how do endpoints discover path properties and how do they associate these properties to the paths? And this has to do with dynamic properties, meaning that they change often, such as congestion or utilization status of some links on the paths. And more static properties, such as capacity of links on the path, or derived properties about a set of paths, such as path disjointness. One more problem is how do endpoints select paths and how then do they inform the network about the paths that they want to use. So in this presentation, I will cover some aspects that are related to the first and the third sub-questions. So the focus of this research group is the endpoint and how to give more path control to the endpoints, meaning more path information and more path choice. But in order to talk about how path control looks at the endpoints, we will have to talk about how the network assists the endpoints in realizing this higher level of path control. So by the term path dissemination, I will refer to three things or three steps. The first one is path construction, and this includes the steps of exploring the topology and then creating paths on top of that topology. And this step can be performed by the network alone or by the network and the endpoints together. The second step is that the endpoint will have to select or choose among these constructed paths. And in the end, the networks will have to inform the endpoints will have to inform the network about which paths to use, something that I will refer to as path representation. So in the remaining presentation, I will talk about design choices about path dissemination, focusing on Scion, which is a security-oriented path-aware internet architecture. And then I will talk about the design choices made in other prominent research proposals in the area, namely NIRA and pathlet routing. So to give you an overview about how path dissemination looks in Scion. The first step is path creation, and this boils down to topology exploration, which is done through a process called beaconing. And then we have path segment construction, namely creating up segments and down segments, which I will explain soon how they work. Then these path segments are registered, and this whole process in Scion is performed by the network. So what the endpoints do is that they start by looking up these path segments, and then they will combine these path segments into end-to-end paths and then select among them. And in the end, they will just inform the network about which paths they want to use. So going to the first step. Topology exploration happens through the process called beaconing. And this process, the beaconing process, starts at core ASs. And the term core ASs is not really well defined, but intuitively consider this that these are ASs that exist high in the hierarchy of the interconnection market, so they have mostly peering relationships and customers. So these beacons will then traverse the hierarchy from top to bottom, from the core towards the edge. And one important thing to note is that each AS will receive multiple beacons, something that will translate into native multipath support and path diversity. So one interesting aspect is that this process of beaconing can be used as a transport medium in order to disseminate path properties, and it is more appropriate for disseminating more static path properties. So in these beacon messages, each AS on a path can input some information such as MTU, capacities of links on the path, some partial path policy, supported services, and supported crypto protocols. Then we have the path segment construction process. And these beacons, as they have traversed the topology, they now contain some path segments that can be used by autonomous systems in order to reach the core ASs that started this beaconing process. So there are up segments, which are path segments that can be used by non-core ASs to reach core ASs. For example, the yellow path segment can be used as an up segment to reach ASK from ASR. And then there are down segments which can be used from core ASs to reach another AS, a non-core AS. For example, the orange path segment can be used as a down segment to reach ASS from ASL. Now, the next step is to register this path segment, because eventually an end-to-end path will consist of an up segment, a down segment, and potentially a core segment, which is a short path segment that may be used in order to bridge the up and down segments. And I will show an example shortly. So these up and down segments will be registered and looked up. And more specifically, an AS will select a subset of these path segments to be used by the local endpoints to reach the core. And another subset will be selected so that other endpoints can reach the AS. Now, these path segments will be registered with a special lookup service that is operated by path servers. And there are two types of this service. First, we have path servers operated by core ASs, and this is where these down segments are initially registered with. And they will serve these down segments to remote endpoints. Then there are path servers that are running at non-core ASs, and they serve a dual purpose. First, they serve up segments to local endpoints, and then they resolve and cast responses of how to reach other remote endpoints. So then we come to the second step, which is to combine the paths in order to create the full end-to-end paths and then select among them. And here we have the lookup of path segments, and at this step we have two translations that take place. The first translation is that the endpoint will contact a name server with a name in order to obtain the AS in which that server resides in. After this translation, the second translation is that the endpoint will contact a local path server, and for that destination AS, it will obtain path segments that can be used that can be combined in order to reach that destination AS. Then these path segments will be combined. And to give you an example, an end-to-end path can consist of an up segment, the down segment, and the core segment you can see in the core to bridge between the up and down segments. Or alternately, for example, if an up segment and a down segment advertise or contain the same peering link, a shorter end-to-end path can be constructed. In the end, there will be multiple end-to-end paths, and the endpoint can select one or more of them for its communication. This brings us to path representation and how the endpoint will inform the network about the selected path. So in Scion, this happens through packet carried forwarding information, and more specifically, this forwarding information consists of interface level instructions. And the consequence of this is that no lookups are required at the data plane, at least for the basic packet forwarding. In the figure, you can see an example of how an AS can allocate interface identifiers locally. So this is only a local process. And now this information, this interface level information, is embedded into the beacons during the beaconing process. And this is how the endpoint will eventually learn this information through the registered up and down segments. Now, talking about some other related research proposals, in ERA, topology exploration and construction is similar to Scion in that endpoints will discover their up graph, which is a set of paths that lead from themselves to the core. A difference is that in ERA, the endpoints are part of this path vector component that is used to discover the up graph. Now, part of these paths will be selected, and then they will register with a name to route lookup service so that other endpoints can look them up in order to construct end-to-end paths. About path selection, the sender will choose a path from its up graph, and then it will combine that up path with a looked up path in order to construct this final end-to-end path. And path representation in ERA is different in that it is implemented through source destination addresses, for example, IPv6 addresses. And these addresses, so the source address will encode an up path, and the destination address will encode a down path. And allocation of addresses in ERA strictly follows the business relationships as the addresses are allocated from providers to customers. Each address at the router is associated with some forwarding state, which is looked up during packet forwarding, similar to how it happens today. So pathlet routing is a more generic routing architecture, and it defines two basic concepts. The first one is vNodes, or virtual nodes, which are created by NAS. And vNodes represent routing structure in the network of NAS. For example, there could be one vNode per router, or one vNode per router interface. Then a pathlet is a sequence of such vNodes along which NAS is willing to forward packets. So with respect to topology exploration and construction, the routers will announce their vNodes to their neighbors, and then the neighbors can combine these vNodes in arbitrary sequences, and they can also combine pathlets and stitch them together in order to create longer pathlets. Path vector is then used in order to disseminate these pathlets and vNodes to the neighbors, but this path vector component in pathlet routing does not enforce any policy, so multiple of these pathlets can be announced to the neighbors. Path selection is not really specified in pathlet routing because as a generic routing architecture, it is not defined whether the endpoints participate or not. For path representation, you can think of MPLS. So pathlets are associated with flat identifiers, and these are put into the packets, and each identifier is then associated with some forwarding state at routers. For example, this can be to push additional pathlets into the packet header. Now, in order to conclude my presentation, this table summarizes the design choices that are done by some prominent proposals in the area. But the important takeaway message is that there has been significant work in this area that answers some of the questions that have been raised by the Path-Aware Networking Research Group. For example, how to provide native multipath support, or how to disseminate static path properties such as link capacities. At the same time, there are many challenges that remain unanswered, so there is a lot of work to be done in the area. For example, how to convey dynamic path properties. How often do we need to disseminate such information? How much information is needed, for example, for obtaining accurate congestion information or latency information? Another issue is how should the endpoint to lookup service interface be implemented? And one more interesting issue is how to disseminate or to convey this path information higher up in the networking stack, closer to the application. And I think some of the subsequent talks will describe some of these issues. So thank you for your attention, and I'll be happy to answer questions.
We have about 5 minutes for questions.
Hello, Tommy Pauly, Apple. So thank you for sharing this. Very cool to see. What I think is most interesting is how you've broken down the various categories and shown the comparisons across them. I imagine for a lot of us, the kind of the Scion architectures and stuff seems quite far off. But I think these principles, when we look at other solutions like what we'll see later on with like PVD and stuff, seem to fall into very similar categories of how these could be represented to end devices and up to applications, hopefully. So I'd be interested to hear your thoughts on what are the necessary things to have end applications get ready for this in a way that allows them to take advantage of some incremental path-aware steps now, but then also have the correct hooks to be path-aware when we have some of these more full visions like you have here.
So I talked mostly about the networking part, so you're talking more about this interface between the network and the application. Mm-hmm. So when talking about path awareness, there are multiple things. So you could have like a fully path aware endpoint, or you could convey some partial information. So if a first step would be, for example, just to give information to the endpoint about the available paths without giving an option to select paths among it. So, for example, I don't know about disjointness of these paths. So it's really a bit hard to imagine based on today's internet architecture. But a first step would be to give information about the current status of the paths that could be used by the endpoints. That could be probabilistic information because it's really hard to give accurate information. But ideally, the ideal goal, I think, would be to go and give the actual control to the endpoint so that they can combine these paths in the way they want. So this gives much more control to the endpoint, and you could see it as being part of the routing architecture, which clearly doesn't happen today.
Tommy, I think you might also want to come up and ask that same question after the next presentation.
Thomas Schmidt, Hamburg. My question would be, how does private peering fit in this picture here? I mean, you wouldn't announce a private peering link in your database, would you?
So it is true that there are some privacy implications for peering because I can go back. So in the beaconing process, if there is a peering link, this peering link would be announced down to the ASs that are below. Something that doesn't happen today. At least BGP provides this privacy. But on the other hand, there are approaches that enable you to determine what the relationship is among two ASs if you look at a few routing tables and see how they look from different vantage points. So this information is partly disclosed today, but I agree with you that this relationship become more explicit through such a process because they're clearly put into the beacons as they traverse the topology.
Yeah, today it's more heuristics, isn't it?
Sorry?
Today it's more heuristics to conclude back from the.
Exactly, that's what I'm saying, that this becomes more explicit. I mean, today this is hidden based on BGP, but based on the heuristics, you can determine what these relationships look like.
But it's also, I guess it's also hidden not only by BGP, but also in the interest of the providers, isn't it?
Yeah, but I mean, BGP, I mean, we're referring to the typical BGP policies, not like BGP as a dissemination method, but through the typical Gower export of progressing this, how these policies are implemented through BGP. So indeed, the providers don't want to do it. And that's why they just announce based on the Gower export model. So you cannot determine this information today just by looking at one table. If you collect this information and you have some multiple vantage points, as happens in research often when we get some data like that, then it is possible to determine this information.
Philip Teasel to Berlin. I wonder how you would represent multiple paths within AAS, as well as multiple, just give me the question.
So what I described clearly neglects this issue about representing multipath information inside an AS. And I would say that one problem is scalability. So interdomain routing gives us a good abstraction to scale this multipath support. One problem of this is that you cannot get accurate disjointness information. So you can have partly disjointness information. And let's say the more disjoint some paths are at the interdomain level, you can assume that there will be more disjointness at the intradomain level if they're purely disjoint, for example, at the interdomain. But if you want to have such accurate information, I think there will be a scalability issue because of the large path diversity that exists inside the domains.
We have a remote. So is that what you're getting up to say?
Nope.
Okay. Don, are you there?
Yeah. Can you hear me?
Yes. Yes.
Yeah, it's from the auto working group. And you may take a look at your presentation at page 12. As you mentioned, the path vector.
Here.
Can you hear me clearly? Sorry. Yeah,
It's not great, but I think you want to talk about pathway routing.
yeah. Otto also proposed an idea of path vector to abstract the routing states of passes. For example, may we suggest that there are 5 routers between the endhost endpoint 1 and endpoint 2, and maybe this the routing state of the 5
Yeah,
routers
so
can
the
be abstracted
dropouts.
to 1.
I'm sorry that you've got enough audio dropout there that we can't understand the question. Can you type it into Jabber? Or turn off video? Or
Okay.
okay, try now.
I don't know how.
So let's go on. If you can type that question into Jabber, Allison, can you relay that if she gets into Jabber? Because I don't think that we've got enough bandwidth off of there. So sorry. Yeah. So Aaron, go ahead, and we'll get the question from Allison.
So Aaron Falk, I worked on a project called FARA, which was sort of a precursor to NERA, which is, I guess, an unfortunate selection of names, but that's clever computer scientists for you. The way that when we were working on FARA, and I think that NERA is the same, although it's been a while since I've read the paper, it was a somewhat anachronistic idea of allowing end users to select their long distance providers when they use the internet. And the whole idea was to give some way of a user to provide hints to the path that you wanted your packets to go. And I just wanted to make that comment because I've heard several comments that were really more about trying to do put fine-grained control of the path that your traffic took in the hands of the end users. And that wasn't really the intent of FARA and NERA. And that the idea was to provide a way for network operators who were far away from either end of the connection to differentiate themselves from each other and therefore provide some incentive for them to compete by providing new services or better quality or deploying new capabilities. And so the point being that it was really about providing some hints so that an end user could express what they wanted, which kind of goes to stuff that's going on in taps. And then this is sort of a mechanism for how you communicate that back and forth. So not a question, just trying to add something to the discussion.
Cool, thanks. Allison, did you get anything on Jabber? All right. If you're still on and listening, Dawn, I'm sorry that we couldn't get your question in. If you could send it to the list, I think Chris is on the list, and we can continue the discussion there. I'm sorry that we couldn't get that working for you. All right, so next is Laurent Chua.
Okay, good afternoon. Laurent Chua, also ETH Zurich. It's my great pleasure to be here. It's my first IETF. I will talk today about interfaces for path selection. This topic overlaps a bit what's going on in the TAPS working group. In particular, I'm going to talk about the sockets API and efforts to replace it, mainly with the post sockets API. And I will try to link this to research perspectives and some research we have been doing that goes in the same direction. So using multiple copies of the same components to improve reliability, availability, performance, or capacity of computer systems is a very old idea. Multi-processor systems, multi-core CPUs, multi-disk storage are all fairly commonplace today. But what about network paths? So I think it's widely accepted that multipath communication can help to improve reliability. If one path goes down, and PTCP, for example, can help to effortlessly and quickly switch to another path. It helps with mobility. If a client disconnects from a Wi-Fi network, for example, he can gracefully switch to LTE, for example. But this is not entirely multipath. It's just switching quickly from a single path to another. And then multipath communication also helps with the total amount of bandwidth. But I think it's not the entire story, and I will try to illustrate that. So some might think that it would be preferable to use a single very good network path than multiple paths. And some might think that this perfect path could be, for example, an optical fiber link. But I think there's no such thing as a perfect network path. Whereas radio waves travel close to the speed of light in vacuum on the surface of the Earth, information only travels about 2/3 of that speed in fiber. So latency is significantly increased when using fiber. And so wireless has this latency advantage, but it also comes with other drawbacks. It has also a mobility advantage, obviously, but it has drawbacks in terms of jitter and all kinds of security implications. So I don't think there's a perfect network path. And also, arguably, in today's internet, there's a fairly limited amount of network paths between one source and one destination, but we don't know what tomorrow's networks will be made of. So there are a number of projects to provide worldwide internet connectivity through balloons, drones, or low orbit satellites. And as we saw in the previous talk, future internet architectures like Cyan in particular will provide more path control to end hosts. And path control means that end hosts may use multiple paths simultaneously. So when I say I work on multipath communication, I hear, oh, multipath TCP. And yes, this is part of the story. Multipath TCP is great because it hides all the multipath communication specificities from the application. So it means that any existing application can use multipath TCP almost out of the box. But it also means that multipath TCP is fairly restricted in what it can do to best fulfill each application's objective. So I also hear sometimes, should we optimize for throughput or latency? Does the application care about throughput or latency? And I think in most critical cases, it's both. So of course, we cannot optimize. It's not straightforward to optimize for both throughput and latency, but I think in most cases, both matter. So a more meaningful question is, does the application need a reliable transport or an unreliable one? So web browsing, for example, latency matters, but the critical requirement is that contents be delivered completely and correctly eventually. And then we have applications that prefer to trade this complete reliability for a very low latency. So for something like a simple request and response protocol, multipath communication might not be the most interesting. The best strategy would be, for example, to send along the best path, assuming we know what that is, or along the best paths. But I think for us, one very interesting scenario was real-time communication, because some applications have very high throughput requirements, and they have also very strict latency requirements. So applications have been using the classic Berkeley sockets API for decades, and arguably it was so successful because it was so simple, but we also think it might be too simple for modern applications and networks. It offers mainly two abstractions, sock stream, so a TCP stream, and sock DRAM for UDP datagrams. But the reality is that the network is not really a file, and datagrams do not offer much functionality. They're mainly glorified IP packets. And then there's a third abstraction, sock sec packets, which is mainly bound to the SCTP, stream control transmission protocol, which is not very common and not extremely deployable in today's internet. And it's multipath, but not really. It's mainly for failover. So here's a a simple example of where classic models fall short. So here we have a source, a simple application that generates a constant data rate of 10 megabits per second, and the messages have a lifetime of 1 second for some reason. It might be a live stream or multiplayer gaming or something. And we have two paths with very contrasting characteristics. On the left-hand side, we have high bandwidth, high delay, high loss path. And on the right-hand side, we have a low bandwidth, low delay, low loss path. And so it's fairly easy to see here that the optimal strategy is to send all data initially on the left-hand side path. And then, because it has a high loss, all the packets that are lost can be retransmitted on the very reliable path on the right-hand side. So using that simple strategy of transmitting along one path and retransmitting along the other, we can expect 100% of the packets to be transmitted before the deadline. And what I think is really interesting here is that even if we had multiple copies of the path on the left-hand side, we still wouldn't be able to achieve 100% because the loss rate is so high. And even with a couple of copies of the path on the right-hand side, we still wouldn't be able to achieve 100% because the bandwidth is so low. So really here, what makes us achieve our goal is path diversity, is the fact that we have so diverse paths. So we address this problem, generalization of this problem to n these different paths, each bearing possibly different characteristics, in a paper that we published recently at DSN. And so we formulated it as a linear optimization. And here we have a similar example with two simple paths, and we can see the result of using each path and using an optimal multipath strategy. So we presented results for both in theory and in simulation with a NS3. So this is one of the reasons why we think it's meaningful and it would be beneficial to have a more expressive sockets API. So the objective is really to have a simple but more powerful API. So the main question now is, what should be the knobs and dials? What should the application tell the transport layer so that the transport layer can make appropriate packet to path assignment decisions? And also, what should be the dials? What should the application be able to learn about the transmission of its messages? Should it just receive the messages when they're ready, or should it be able to? So that's more of an open question. What should the application learn about the transmission of his messages? So again, this relates to the work that's being done in the TAPS working group with post sockets. So I will not go too much into the details of this, but post sockets is a transport platform and language independent API, which supports a dynamic selection of transport protocol stacks in an explicitly multipath environment with a message abstractions. And there's a concept of long-lived associations, which are composed of one or more paths. And there's an asynchronous reception of messages. So I will mainly talk about the properties that the application can set for the messages. The first one is the one I've already talked about, so lifetime or deadline for partial reliability. The second one is priority, or more exactly niceness, which express which messages should be delivered first. Then there's dependence, specifying if other messages should be delivered beforehand. Idempotence specifies whether it is safe to send in situations that may cause a message to be delivered more than once. And immediacy is just to say, do not wait to combine this message with other messages or parts thereof. So again, about lifetime, I think TCP versus UDP is often a false dichotomy. There's something that lies in between, and that's partial reliability. So packets with a lifetime can be retransmitted, may be retransmitted, but only for a limited period. I think this is a meaningful property because, as I said, we cannot optimize for both latency and throughput together. It's typically a trade-off. So that's one way to specify strict latency conditions. And there exist transport protocols that use this concept of partial reliability. There's a partial reliability extension to the SCTP protocol, and there's a variant of TCP called the line-aware data center TCP. Then there's niceness, which is just the inverse of priority. And so it goes together nicely with lifetime, because as both lifetime and niceness increase, priority decreases. So niceness is sort of the equivalent of lifetime for reliable transport. And by default, it's 0, meaning that by default, messages should be delivered with the highest possible priority, but then it can be reduced arbitrarily. And the last message property that's really relevant for path selection is dependence. A message may have antecedents, specifying whether other messages must be delivered first. So for example, a web page should preferably be delivered before embedded media, such as images. Then aside from message properties, an application may want to set policies specifying which features of the transport protocols it prefers, or which paths or interfaces it prefers to use for cost, performance, or security or privacy reasons. There are multiple domains to do that. It can be at the application level, or it could be a user policy or a system policy. So the first example is that Wi-Fi might be preferred to LTE for cost reasons. The second example is that an application might require that its messages do not cross certain networks for security reasons. So putting everything together, I think fairly hard problems lie ahead. So this is a graph we obtained when we solve this optimization problem. And we see that when we have a high number of paths, in this case, when we have 10 paths and we consider 3 retransmissions, it's a computationally hard problem to optimally assign packet to paths. So that's the bad news. But the good news, I think, is that assuming that path characteristics are fairly stable, the problem is not necessarily solved for each packet. Then the other piece of good news is that not finding the optimal solution does not mean that we cannot find very good solutions with heuristics and simplifications. And finally, I think that more expressive APIs, such as the post-sockets API, could drive a new multipath research and a new kind of multipath research. Thanks. So yeah, thank you for your attention. I'll be happy to take questions.
Hi, Brian Trammell, not as chair. So I have 2 quick questions. Actually, could you go back to your last slide? It might be a little, I could see it from over there. It might be a little bit hard to see, but yeah, that's linear number of paths on the bottom and logarithmic time for computation. So yeah, clearly we can't do this for every packet unless we have more than 2 paths. And it might there might be an optimization loop that you can do here where you could say, okay, well, I'm going to limit the number of paths just arbitrarily in order to, but okay, that's scary, but that's why it's research. Let me PostSockets co-author TAPS participant hat on. Let me see if I can, let me phrase a question, and I think the answer is yes. So the difference between what we're doing in TAPS and sort of what you're doing with PostSockets on top of this transport selection engine is we care about selecting this, in TAPS we care about selecting the stack and then saying, okay, well, we have this abstraction so you don't have to rewrite the application when you go from stack to stack. And you're more interested in using the message properties in order to go on a packet by packet or flow by flow basis as to how you do the transmission. Okay.
Yeah.
Cool.
Yeah.
Chair had other questions? Actually, let me get a show of hands. How many transport people in the room? Okay, so this was kind of review. Good. That's good feedback from the chairs. Cool, thanks. How many routing people in the room? All the way in the back. Okay, a couple up front. Good.
Eric? Hmm.
Okay, my name is Rick Vink, and I'm speaking in the name of many authors. At least two of them are in the room, so Pierre and Tommy are here, maybe others. We're presenting at the Interea something called provisioning domain that can have some intersection with the purpose of this research group. For instance, nowadays networks are becoming much more complex than they were before. Now, if you look about the PC, which is there, it's coupled physically to 3 networks. It can be associated through the phone doing tethering over Bluetooth, can be connected to the Wi-Fi network of the enterprise, and can be a wide connection to the enterprise as well. The enterprise itself can have 2 service providers, giving 2 different paths, including connectivity to, let's say, an IPsec VPN. So at least 3 interfaces here, and at least 4 paths actually to the internet. 1 via the phone, service provider 1, service provider 2, and the VPN. So how can an application select the right thing? In the old world, the legacy world of IPv4, maybe some of you are still using it, but I hope no. How do you do it? As soon as you selected one path, you do not to ensure that the return traffic is going by the same path. Okay, selecting one path is correct, but in some cases you want to have a symmetric path. So we need to find a way in IPv6, because in IPv6 we don't have NAT. We don't want to have NAT, because that would be a stupid idea. Similar stuff, a problem that has been raised in the home networking group at the last IETF by Ted Lemon. If you have 2 interface or 2 IPv6 prefix, and you select, you resolve, let's say, IETF.org by using the LTE interface, you will get the Cloudflare CDN the closest to your LTE provider. In my case, it will be something in Brussels, in Belgium. Oh, and now I want to go to this IETF.org address via my Wi-Fi here. So I will need to travel from Singapore to Brussels, even if Cloudflare and a POP and a cache here. So we have multiple aspects here how to select basically a path or an address. We can use it the same another way, even if you have a single interface. In IPv6, you can have multiple addresses per interface from different prefixes. In this case, coming through the same router, but could have been coming from 5, 6, 7, 10 routers on the same layer 2 domain. Now, by selecting the right source address, then the network itself can route the packets through traffic engineering, SRv6, normal RSVP-TE or whatever, or selecting basically LTE or satellite or whatever link. So we need to make the application aware about the existence of multiple paths, basically traffic engineering, quality of service. So how we do it? There is a concept already for a couple of years at the IETF, by this RFC 7556, that describe a provisioning domain. A provisioning domain is basically the consistent set of information that you can use to connect to the internet. Mainly, one IP address, one interface, one DNS recursive server, maybe a DNS search list, a next hop, and a few things like MTU maybe. Now, until now, most of the network, I mean, computer in the 80s, it had only one connection. So by default, it was a single PVD, no choice for the application. Now, I see in the previous slide, you may have or you must have multiple choice. So you must have multiple PVDs, and we may want to name them. And this is part of this draft to put a name to a PVD. So an application, for instance, can select one specific PVD and will get a specific set of consistent information. And in the same shot, we are extending the notion of PVD, which was just layer 3 information, layer 2, layer 3 information, to go to the application layer by doing a two-stage, let's say, PVD provisioning. I don't want to go into many details about the protocol. It's not really the purpose of this session here, but it's simply sent over an IPv6 router advertisement. We are adding a new option there, and there's only two fields interesting for this group. The PVD ID, which is used in the kernel to identify which PVD you want to use, which is, by the way, and it's not a coincidence, it's on design, a fully qualified domain name. And you will see why. You also have a sequence field. And the sequence is basically to say, hey, I have new information for you. This is version 5. Then maybe 1 hour later, 2 weeks after, 2 seconds after, you will send version 6. It's a trigger for everyone receiving this typically multicast route advertisement to refresh all the information. Why do I say refresh? Because it's two-stage. So in the array, you receive the layer 2, layer 3 information. And then based on the fully qualified domain name, you use HTTP over TLS and fetch this well-known URL that contains a JSON file, that contains some metadata or application data. So there's an example here of this JSON file. You can have a name which is more readable than a fully qualified domain name. It could be even a localized name, put it there in French, but it could be in Japanese, Korean, or whatever, to help the end user to make a decision. But we can also put there some characteristic of the network. Until now, we only put the first hop. So let's say between the CPE and the access network, because typically you know the maximum bit rate and the minimum latency. If it's a satellite link, you know it's a couple of 10 or hundreds of milliseconds there. But there are other examples. I don't know whether you can read at the bottom of the slide, but we can say, for instance, that's a captive portal. That's also important for the application. If you have an IoT device that needs to upgrade to upload its results somewhere, obviously it cannot traverse a normal captive portal. So there's no point of trying to use this address. Is it metered? Yes or no? Meaning, is it free or not? Okay, and a few things like this. So this could be an opportunity as well for this working group, my research group, sorry, to propose information to be put there. And we will be all ears, of course. Currently, we were thinking, just an example, not sure whether it will be finalized in the PVD when it becomes a standard. The cost, for instance, on the network access, for now, it's a little bit too complex to handle it, but for next revision or whatever, an extension. As I said, what about the bandwidth between the CPE and the access network? Typically, it's known because if you're using VDSL, you know the which speed the VDSL modem is synchronized. Captive portal walled garden as well. All of us will take the plane, I guess, to fly back home tomorrow or the day after. In most of the airlines, you get a free Wi-Fi only to go to the VOD, right? The video on demand. That's free. If you want to go to the real internet, you need to pay. So there's a specific characteristic as well for this thing. Now in a plane, you don't have a choice anyway, so maybe less useful. So we have been working on this for about a year. Other authors, by the way, are from Apple. There are people from Google interested, and Microsoft is interested as well. So there is a big momentum behind it. So at Cisco, where I'm working, we have public domain implementation. The URL is there with partially working Linux kernel, including a user space daemon, because that's where we need to get the application, the metadata. We have a Wireshark dissector. We have modified ERA-DVD and ODHCP for OpenWRT and LEDE to work. And we, of course, we have implemented this information sending into the router, not yet shipping, of course. Maybe a specific thing to say. We are working as well in a project called NEAT, the H2020 project from the European Union, where basically they want to implement a firmware like a post-socket API, right? And we have some meetings as well with Brian on this 6 months ago, something like that, to kind of synchronize the effort. Where this API, you can ask, the application can ask some properties. I request low latency, I request security, for instance. And based on some characteristic of the network and some paths of the network, information about the network, try multiple transport, UDP, TCP, SCTP, DTLS, or whatever, or quick, and find the best compromise. Of course, this is by default done on information coming only from the open operating system, from the kernel, but with PVD, we can provide some additional information coming from the network. So there is a good intersection here. So that's basically what I wanted to say today. So there is a way, there is a need as well for application to select the path, maybe not the path in the sense you mean it, but I think pretty close. Because one information we can receive by PVD is also the segment routing header to be inserted in all the packets if you select this service. So then we select the real path of the network. Any question? Oh, you can sit there.
Hi, Brian Trammell. So nasty question from somebody who has kind of been aware of this PVD work and now understands it. So thank you for the presentation. This was really cool. This basically gives you a less hacky DHCP options like interface for non-DHCP v6 networks, right? Okay. That's good.
It provides way more things. It's way easier to extend as well.
Right. Yes. So less hacky because like you can hack DHCP v6 up to a certain point, and then you run out of hack space. So you have a lot more hack space here. Actually, I think I should probably take the rest of these questions offline because these people don't just need to see us have a really long conversation about this, which I now want to have. But I have an architectural question about PVDs. So the information that's there right now is basically architecturally limited to the first hop, right? It's just about your access. And then anything that was sort of as part of if you wanted to implement the first n hops of a path-aware network with this, your first hop would be PVD, the next n hops would be segment routing, and then you'd have to do some magic to go inter-domain at this point, right?
That's correct. I mean, now, we could extend PVD to get more information deeper in the network, but I'm not really sure whether it's sensible in 2017.
Yeah, okay. And there's another question I'll save for you for the open mic.
Okay.
So cool, thanks.
Tommy Pauly, Apple. So I'm co-authoring this as well, but I would like to just solicit feedback from anyone else, especially the presentations we saw earlier on how they could see this type of thing fitting in. I do think there is overlap of especially how we could imagine applications viewing the network, viewing things through PVDs. To Brian's point, I think it's key, how do you let applications see the PVDs? Right now, we are focused on one hop because that's all we can really do. But to some degree, the fact that a router is telling you that it has multiple uplinks is actually multiple hops behind you. So your first hop is telling you what it knows about the next ones, and those are represented as separate PVDs. If, for whatever reason, your router was able to learn about more fancy things and it could actually control your routes through a Scion architecture, if applications were aware of PVDs, those could just show up as maybe 25 different PVDs, and maybe there's a scalability problem there. But hopefully, each of these would be self-contained version of information. Because beyond the extended information, one of the really key things of the PVD is just the ability to say, there is something different here. There are two things. Even if you don't know what they are, you can try probing on them and just use them differently.
Yeah, perfectly.
Thanks. And Tommy, let's take that first question to the open questions session. I want to come back to that. So who's next? Oh, yeah. So Sabine is next.
Yes.
Where's the? There it is. So.
So, hello everyone. So there has been
A little closer to the mic.
Sorry.
You have to. It's uncomfortable, but.
Okay.
Yeah.
Okay. So there has been a summary of open questions that was circulated last week. And Alto is actually addressing the ones in the green color, basically about how path property can be exposed to applications, plus a bunch of questions that were raised on the mailing list, particularly regarding mutual trust between applications and the network, and privacy concerns, and also level of abstraction. So the IETF protocol is a transport protocol that exposes a network-centric abstraction of the network. So the goal is to guide the application for the selection of their endpoints so as to trade network cost efficiency with equal or better application performance. So this way, to this end, the Alto exposes via RESTful APIs information services that are the Alto network map, which is a set of network locations that network location groupings with provider-defined identifiers and enumeration of the related endpoints. So the provider identifier may be expressed in natural languages. So it's an indirect and network agnostic way to aggregate network endpoints that share some common property or characteristic. So the second information service is the Alto coast map, so that exposes coasts among the PIDs and the endpoints of the map. So again, these costs do not need to be the real values, because that will never happen. Everybody knows it. But typically will be an abstraction on real costs that give some hint on the network performance. It can be an abstracted cost. It can be ordinal values. So the base protocol, as shown here, is abstracting the network. Abstracting the network. I don't know if I have a pointer. So here, for example, here is the, sorry. So here is the real network, and it abstracts this in kind of a single switch abstraction with the flows here, the end-to-end points here, and here in this example. So it exposes one path per destination, and within this path conveys one single cost metric. So, well, Panrg, we may say that is actually looking at how to connect. So whereas the base protocol is looking at where to connect. So the Alto working group is specifying and working on a number of extensions to address this aspect. So they mostly build on an extension that is defining abstractions of network traffic engineering-like or network performance-like metrics that can be, of course, abstracted. So let's go quickly through those extensions. So you have one extension that is called AltoPath vector. So the AltoPath vector abstraction details some, within a path, in an end-to-end path, it details some parts of the path that the network considers as significant, and it describes them as like abstracted network elements, which is a set of one or more switches or links or any part of the network. And the ANE properties may be exposed by the network in a separate property map. So here, for example, so you have now some detail on the path, and the application, when it gets the fact, for example, that from this point to this point, the routing or the path goes through these particular steps, and the path here goes through some other particular steps, it can figure out whether, for example, they share a bottleneck, and so and figure out what performance or what capacity it will get. So the second how to connect kind of extension here assumes that there are several paths available to the application, in part, namely paths that relate to the access type. So here, for example, the application knows that it can connect via Wi-Fi or cellular, so it requests a path performance given its access type and SLA, and here it gets, for example, two values. If I ask cell and SLA 3 and Wi-Fi and SLA 3, so then here I can get two values and figure out how to connect. Given that you do not have necessarily a better quality with Wi-Fi, and now with 4G you often have you're better off, and if there is any special on the weekend, you're better off using a cellular connection. The other, another extension there is called multicast with constraints. So a multicast, with multicast, I can request, for example, routing cost and bandwidth capacity on path that I would like to have with either lower routing, lower cost and lower bandwidth, or higher cost, but then better bandwidth. So I will ask for those two metrics, and the Alto will return values only on those paths that are meeting the constraints. So this way it's kind of selecting, telling me, do not use that one path. So besides the how to connect, if it may be of interest to the Panrg group to have a service, an information service that help applications to decide when to connect. And this is done with Alto cost calendars. And so here you have an array of time-dependent cost values. And here you have attributes that help you to interpret those values in the array. So, and here are the references, and thank you for your attention.
Thank you very much. Any quick questions on this? No. Okay, so thank you, and we'll go to the next lightning talk. Yeah, just gain is high. So good.
Hi, hello everyone. My name is Joe from Huawei. Today my topic is path awareness for congestion control. Congestion control without path awareness. Basically, there are two main methods for a host to know the path when there is no path awareness. The first one is by assumption. The host, when they think the network is congested or is getting congested, or is broken when it found the event of packet loss, or RTD increasing, or ACK lost for quite a long time. Another method is by measurement. When the host get more throughput by increasing sending rate, then it may think the network is on the night node. When it get more throughput by decreasing sending rate, then it may think the network is congested. Then congestion control with path wireless. ECN explicit congestion notification. Currently, ECN is the only standard way host use the path properties feedback from network node for congestion control. It gets good throughput and latency in data center network with rough information. Continue more rich and accurate path properties. In our research for networks, it is found that some dynamic networking information from a bottleneck device on the path is very useful to the congestion control. Like with the properties such as ingress rate, egress rate, buffer length, feedback from bottleneck node, we could get a higher bandwidth utilization and low latency as shown in Figure 1. In Figure 1, we can see the accurate feedback method as red line could occupy the available bandwidth very faster than the legacy method. Another finding is with properties of radio link state such as radio quality, spectrum utilization at a LTE base station or Wi-Fi device. We could adapt the variable wireless network very well as Figure 2 shows. In Figure 2, the red line is the capacity of the wireless network, and the black line is our method. We can see the black line could adapt the red line very well than other color. Then how to distribute the path properties. ECN use two in-band bits for information distribution as the IETF standard. But for rich and accurate properties, there is no standard way now. We only could use the TCP and IP options for distribution. But this method is limited by the option length and has lots of problems with the mailbox as well. So we may prefer a standard in-band way to distribute these properties between path and host. Specific sublayer between TCP and IP maybe it's better, like layer 3.5. And more of path awareness. So before path awareness, host has no idea about the path. After path awareness, host may know the path, then could select the right path and use path more efficient than before. So could we do more about the path? Could we control the path properties? We have this idea because we found the service like Live via Air, which needs ultimate properties, like very high bandwidth and low latency. This kind of flows cannot only depend on the best effort network or better selection of a path. They may need to control the path properties for them, like path resource allocation as the flow setup and release as the flow's exit. So that's it. Thank you.
Thank you very much. Any questions on that? No. Okay.
Yeah. So yeah, it's your turn.
So now people won't actually try to use it as a mic stand. Oh, Dawn, can you beam her in? Joe, can you come back? I think there is a question.
Hi, can you hear me? About the page 6 that said when the application wanted to control the path properties, I think this might be unfair because what if more than one application want to control the path properties? How would the network do the resource allocation?
Yeah, but for this kind of like via AR, this most valuable service we can do this kind of control properties for them. Just for some cases, not for all the cases.
You say that assign them with the higher priority?
Not just priority, but some resource allocated for them.
Okay, thank you.
Hi, I'm Brian Trammell, in case that wasn't obvious by now. I put together a little draft a little bit before this meeting, sent it out to the list, I think about a week ago, based on, so the idea is basically to try and focus a little bit of discussion on the list, get, maybe something going, about what I think the questions are in this space. And there are 6. We have some questions and we have some more questions. So I'll just go through these very briefly. So how are path to properties defined and represented, right? So you could call this a closed question, right? Everything that does anything in exposing path or even last hop information to the endpoints must have its own vocabulary in order to say, right? So Alto has the cost maps and the network maps. The PVD has this extension thing where you have key value pairs, and some of the points in this key value pair space are assigned. So for example, this is, I think, metered is one of the things, and that has a meaning. I think it seems to me that all of the work sort of coming from the IETF side has, I don't want to say arbitrary, but they've kind of gone for the most obvious way to represent those properties for their use case. And it's not clear to me that in a fully path-aware network that that's the best way to do it, right? Like, so Alto is focused on a particular application space. PVD is focused on a particular application space. All of them are built in such a way that a common vocabulary could be built into them, right? It's not, they all have points of extensibility that are exercised to the point that you could use them. But it seems like it's interesting to step back and consider what those what these sort of vocabulary items are and how what they mean, and how the definition of that space implies what we can and can't do with path-aware networking, implies sort of like whether we can or cannot deploy it. So we have a couple of other questions. How do endpoints discover trustworthy path properties? Scion represents a point in this design space. So does Alto for the set of path properties that they care about. So we have sort of like running code here. We have solutions that we think that we can take from there. How can endpoints select paths to use for traffic in a way that can be trusted by the network? So this is really okay. So this gets, I think, a little bit back to Don's question. I've said something about path selection. Why won't we just run into the DSCP problem of mark all of my packets really, really, really important because I want to go to the network very fast. My computer is telling me to sit down. Okay. Please confirm your German. Okay. So in here, like as we saw from Chris's talk, there's running code on these for both addressing-based approaches and PCFS-based approaches. There are ways to do this, right? So Scion represents, again, another point in this design space. How can interfaces of the transport and application layers support the use of path awareness? PostSockets, which is TAPS, seems pretty clearly set to this. But there are 2 other bigger sort of higher layer questions that I think we should address probably here. One is, how can a path-aware network and a path-aware internet be effectively operated, right? So the network operations model that we have right now is you tell BGP where you're willing to accept traffic from for which prefixes, and magic happens and you get traffic on inbound interfaces, and you can change your announcements, and you have a effective and predictable control loop. Well, okay, predictability in BGP is an open area, but you have an effective control loop for being able to say, okay, this traffic's going to come here. I want this traffic to go away. I'm going to stop announcing that prefix on that interface, and the traffic goes where you tell it. In a path-aware network, the endpoints that are attached to the network are also making decisions about which path they're going to use. To some extent, this is already happening in sort of like in multipath networks right now, in multiply connected networks. The endpoints are mobile, and they are shifting traffic from one interface to another, sort of in the degenerate 2-point case. So this might be a problem that we in the internet engineering community have to handle anyway. And this framework might give us a way to think of that in a way that we get a better handle on it. But the operations model is a completely open question. And it would be interesting maybe to have some ops area input here or people who work in the management space to come in and help us out with that. The second one is really a layer 8, an economic layer question. How can the incentives of network operators and end users be aligned to realize the vision here, right? So why, as this was actually a question that was posed to me by Martin Thompson as soon as he read the draft, like 5 minutes after I posted it. He's like, why didn't you consider this? And I'm like, thank you, Martin. It's in GitHub now. So yeah, the working copy of this in GitHub actually has this question, and we'll post that and any other questions that we enable dictation language, German. Und dann werden wir das am nächsten, sorry. And then we'll post that after this meeting. If there are any other open questions that people want to come up and address. I obviously have fuzzy ideas here. That might be a document that we talk about, but we need to have an answer for the question, why would somebody actually buy a gateway that would do this? Why would they buy a router? Why would they offer this service? There has been some work that I'm aware of that's been done in this space in Scion, and maybe this would be a venue to talk about that as well. That's my piece. Does anyone have clarifying questions on the questions? Are there meta questions?
Lin from Huawei. I think these 3 topics are huge, and I just want to ask the smallest question. For the path selection, for address-based selections, are you referring to the source routing?
Well, I mean, like, so we use address-based path selection right now all the time, right? You have a destination address, and that implies a path. You just don't get any information about it. But here I'm referring specifically to segment routing.
Yes, segment routing. So for the V6, definitely we can do it. But how about V4?
Why do I care about the legacy internet?
No, V4 has a lot of deployment right now, more than 80%.
Yeah, right now.
Yes.
Yes.
And the growth very slow for IPv6.
Yeah. So let me actually take, before Lee gets up and causes something that I have to talk to the ombuds team about. Down Lee. Let me just give you my personal feedback. My personal view on that. It does seem to me like there are a lot of enabling technologies that work much better on V6 than on V4 for this sort of thing, right? You could build, like, you could replace PVD with some hacks in DHCP. You could, oh, are you going to design this for me, Aaron? Or are you going to go talk to somebody about the feedback? Okay, perfect. Yeah, thank you. So I actually see this as if this is something that V6 does much better than V4, right? Like, if you saw the API talk that Laurent gave, we're actually talking about having to rewrite all the applications anyway. So moving to V6 is not going to be harder than rewriting all the applications, I don't think.
Lee Howard. So I could imagine trying to build in a description of NAT zones, if you would, or NAT domains, saying this is, we've got this instance of private address space.
Yeah, I call them addressing contexts when I've written about this.
There you go. So I could imagine, so that's conceivable. I'm not sure the work's worth doing, but that might well come out of the essentially applicability statements that you're talking about in the last couple points here.
Right.
Which I'd love to see, hey, how is this work going to be useful, being one of the early questions. So thank you.
Okay. So I'll actually point out again, so another thing that just came to mind. So I know that Scion actually does work with V4, right? So it basically uses Scion routing through the internet, and then you can have the last hop addresses be IPv4 addresses, and it just hands off in the endpoint AS to V4. So there's a way that you can use an overlay thing to get V4 endpoints talking to V4 endpoints over Scion, but that's kind of a life extension hack for V4 as I see it.
Shweta, Cisco. Regarding the open question on how the path-aware network will make use of path-aware network, that would also probably influence the properties of the path that would be collected if the network has to make use of the path-aware network rather than the applications. Wouldn't it be?
That's a really, yeah, so you're basically talking about, so I see that as an intermediate stage, right? Like, so you build, like the way that we often build these new technologies is you go local net to local net, you do the tunnel thing because you own bits of the tunnel. That's a really good question, and I don't have an answer, but that should get written down in this document actually. So, you know, how are these affected by, like, so where like all of these properties, so, you know, things like Laurent's work wouldn't work there, right? Because you don't have enough information to say the application can't go, okay, this packet, or the transport layer can't go, this packet goes here, this packet goes here. But what do you know, what are the benefits, and then what are the changes in the model when you go from a local to local net as opposed to endpoint, or maybe even local net to endpoint or endpoint to local net? That's a really good question. So I will go off and think about that for this document, and I invite you to help me out.
Another comment, just for completeness, we are doing this work in IPPM as well for collecting
the IOM stuff.
IOM stuff. Yeah. That would probably, I mean, there is no encapsulation defined for it, but it defines what could be collected, but that's mostly focused on how you can operate your network better and feed it back into the application. I guess that also has to find some place in case if we go with modifying the transport protocol to carry and return the data in the transport in Quick and TCP and so on. That would probably be one other way of returning the data for awareness, for the application awareness.
So it seems to me that the IOEM stuff could be used sort of in the interdomain, or the intradomain, but also in the interdomain. Like, so IOEM. Well, actually, right now IOEM is explicitly single domain or single IOEM domain, where that doesn't necessarily overlap with an AS, but usually does. So that could be used as a way to measure dynamic properties in a way that could be then disseminated through a path dissemination protocol like Scion. Yeah, that's definitely a part of this. I put that into the gigantic bin called enabling technologies, but yeah, that makes the measurement part of this much easier. That's a good point too. Sure. Thank you.
Could you go to the next slide? Yeah. So on the last question, I'm very glad that, sorry, I'm Tommy Pauly. I'm glad on the last question that Martin brought that up. I would be not at all surprised if that was also related to the fact that, you know, he is chairing the captive portal stuff. And when I heard that question, the thing that immediately came to mind was that, because that is a very clear example of a weird incentive situation in which there already are quite unusual network properties that we want to be aware of. And it's not necessarily multiple paths, but it is one path with funky properties that we want to know. And what are the incentives around even that existing case, the network's letting us know that they're doing evil things to our traffic to hijack?
Because the whole business model is based on the evil things that they're doing.
Right. And so the one thing that brings up is, you know, as we are trying to build a solution for captive portals, hopefully there's some sort of compromise that is mutually not terrible, that allows the network to communicate the terrible things they're doing to block the device, but also enable the system to help show their ads a little bit better, which is kind of terrible but important. So as we're looking at this, right, I imagine that some of these incentive questions will be very fraught with compromises between lots of parties, and that is a necessary part of this.
So I'll say that I didn't want to bring this up at all, but Aaron kind of already did. That one of the things that having, if you have path property dissemination in a trustworthy way, so those are secured, and you have path control in a trustworthy way, so each participating AS can know that the path isn't forging anything, right? Like, so you're in a situation where we've basically made KC's wonderful spoofing detector obsolete, which would be awesome because I'm sure she doesn't want to have to do that. Then you actually can enter into business relationships with ASs that you're not directly connected to. Is that a thing that's enough of an incentive to get people to put these things up? Maybe. I don't know. But it seems like we're changing the business relationships that you can build if we do this. And that sets up, that takes this problem from the complexity of the captive portal thing, where it's like, it's pretty clear how you can analyze this, because these guys are trying to screw you as hard as they can, and you're trying not to get screwed. You know, you can kind of meet at an equilibrium if maybe that equilibrium space is 0, but there might be points in that equilibrium space. Here, by basically changing the way that you can build business relationships, you throw this into a giant, I mean, like, this is now an economic problem of a complexity that I'm certainly not enough of an economist to solve.
Yeah, I think that, yeah, the points that Aaron brought up earlier about the point of doing this path awareness is potentially just to create an open market of paths that you can get to, is really interesting and really points towards having multiple paths as being maybe a way out of some of the terrible incentives that we have today on locked paths.
Any great oughts want to get up and grumble about ATM? All right, so that's I guess we've kind of already gone into the open questions part, so I guess mic lines are open. I'm putting my chair hat back on, and I'm going to pick on Tommy. So you asked Laurent and Chris a question. Could you restate that? Because I forget what it was. I just remember it was your first question of, no?
Tommy. So I don't remember exactly what it was, but I think the first question that I had given to Chris was essentially that, you know, we're seeing that a lot of these patterns between the various protocols and the various architectures, Scion or PVDs or Alto, have these similar patterns of how we do path discovery, path communication. And we also brought up the point of APIs and how our applications interacting with these. And we could design kind of the perfect API for each of. Yes, exactly. Right. So I think this is a really good table. And when we look at the APIs that we can design, whether they're post or neat stuff, I think those overlap. But we've also often defined the APIs to be very specific to the problems we want to solve in that case. So maybe we can make it more general, but how do we evolve this to make sure that, let's say today I can write an API for PVD that works on my multi-homed IPv6 networks, and can I use those same properties to work on Scion network when it comes along? Like, what's the transition path for this? Is there a difference between kind of soft path-aware networks in which I can get away with just knowing a little bit, and maybe a world in which path awareness is critical to be able to use it well? So how does that work? I don't know.
Do you have anything you want to say on that? Or I think I'd take that down as an open question, but if anybody from that table there has a comment, feel free to make it. I think it's an open question. I think it's something we need to go think about. Cool. Any other questions on this, or should we kind of try and wrap this up and figure out what the next steps are? I know I've learned a lot. This was interesting for me. I don't know. I hope it was interesting for you. Let me put my chair hat back on then and say, so we have one action item here. Spencer is still here, so we can reiterate that he's going to write us a draft. Well, he's going to write us the start of a draft that we can then point at other angry transport people and have them contribute. So I can put this back over on the non-functional mic stand because I have my own mic over there.
Just, you know, assuming that the chairs are not looking at the mailing list because they're looking at the meeting, I did send a note to the mailing list about that, just making sure people can find me and asking them to send me the names so that when I have a good template, I'm going to do my two first and see what information I need to ask for, and then I'll circle back and ask them. But I just want to let you guys know that.
Could I ask you, as a one of the chairs of this afternoon's TSV area session, to plug that effort over there as well?
At least me or Miria is awake now.
Okay.
I'm not sure that we both are.
Okay.
But yes, that would be lovely.
May I remind you if you forget?
I need to put this on the IETF and IRTF discuss list that basically anybody can remind me of anything at any time.
Okay.
Thank you.
I heard a couple of bits of input for the open questions draft, so I will rev that and send it to the list soon. I actually want to get a little bit of a sort of a sense of who's in here as the chair. Who here has no idea what's going on and is willing to say so? Okay, Aaron. Do you find this area interesting and useful, and you think you get kind of a handle? You don't really have to have. It's not like a BOF question where it's like, do we understand the problem? Because the point of this is that we don't understand the problem. Does this work interest you? Just a sort of a show of hands. I mean, are you here for this, or are you here for the internet and the air conditioning? Okay. Okay, a few hands. Good. Are you just here to troll people who like IPv4? All right, so I have what I need as chair to figure out what the next steps are. We'll put together an agenda for London.
We actually already have at least one talk, right, so if anyone would like to present, let us know.
We're also looking for suggestions for what the general theme of that agenda should be. Like, so these were sort of the first two. We're booting the research group ideas, and we'll try to keep the energy going. It's much fewer people in here than last time, I noticed, because the first meeting of anything is like, oh, what's that? I'm going to come sit down. So hopefully we'll have about this, we'll stabilize the count of people in the room by London. One thing I do want to make sure that we note is that for London, we should try to conflict out everything in routing. Because I know too that most of the apps people are over in Do. And the problem with basically trying to do a research group that ends up being glue between applications and routing via transport and internet is that the only people who can show up here are the IASA 2.0 folks and the transport area, which we mostly conflicted. So
yeah, I think speaking with my this is Allison with my RTF hat on, I think you have to probably put like way more primary conflicts. And you might end up on Friday, but and just tell everybody if you come on Friday, right?
Right.
But the other thing is that you could consider having two sessions and kind of bridging between them, if it's to allow for some different perspectives on this. We would allow you to do that.
Okay. So two shorter sessions.
Two shorter sessions that have different conflicts, and then the chairs work on bridging them somewhat so that people can catch up, give them some catch up between it. Because I think it's going to be impossible. At some point, you'll probably want to plan an interim where you can actually dive down in deeper, and that'll be a good thing for you. But it's kind of impossible to avoid the problems of the scheduling here.
Yeah. So I see there's sort of a smallish group of people who would definitely contribute that we could do an interim yet, but I don't think we have a long enough list of work to make that productive.
Yeah, I agree with that.
So I think we can once we have a scope that makes sense to do, that's a really good idea. I guess we give them some time back.
And before people could leave the room, there must be blue sheets somewhere. So raise your hand if you have not signed them yet, please.
And there's another one somewhere.
Another one somewhere. I'll find it.
Okay. Yeah. Maybe people took it over to Do and they're signing the Panrg blue sheet in Do. That would be cool. All right. So with that, thank you very much for coming to the second meeting of the Panrg, and we will see you in London on the mailing list. Hey, Kyle. How you doing?
The big thing I think it seems like the big thing this is going to address this is legitimate fears and operators.
Yeah.
But also reducing the flow.
Yeah,
We
so
need to
the-
figure out how much is built is.
Yeah. Right. Yeah. Okay. So,
in a situation where the operator has to,
like,
push
the
it back and try and
IETF
save
and
it.
IRTF are trying to kill my job.
Yeah.